Second speaker is the Catherine Graves from the Hewlett-Packard. So she received a PhD at applied physics from the Stanford University, and she was working study ultra-magnetization reversal in a ferromagnetic material for the future computer memory application. So now she is a research scientist at Hewlett-Packard Lab, and she is developing the next generation analog and neuromorphic computational accelerators using the Memristor devices. Memristor devices, the new devices. So, and she is interested in how the nanoscale analog and dynamical electronic devices such as the Memristor can accelerate the core bottleneck of the computation, such as the recent project to accelerate the matrix multiplication with the dot product engine. So please join me in welcome to Dr. Graves.
Thank you very much for the introduction, and good morning, everybody here. And it's really a pleasure and honor to be here, and I'd like to thank the organizers for supercomputing for having me here, particularly since I'm going to be talking about something pretty different from what you've been hearing this week, which is doing computation not in CMOS. And instead, what I'm going to be talking to you about today is using the inherent physics of different systems that we've designed to do computation for some core bottleneck operations, and to do that computation at lower power and at higher throughput than you can currently do it. And so I'm going to be touching on some themes for analog computation, neuromorphic computation inside our lab prototype accelerator that's called the dot product engine. Now you might sort of just be wanting to check in with yourself for a minute and say, well, are we really at the point where we need to talk about post-CMOS and doing computation not in sort of these conventional ways? And really, I don't think I need to do too much to convince the audience here at Supercomputing that compute and memory is not really keeping up with where we want it to be. I have some examples here, but I've just heard at talks this week about even more crazy examples for this, for where we want to go and things we want to do. I think one of my favorites was on Tuesday with Professor Windus talking about even with exascale systems, we're still not within reach of being able to do molecular dynamic simulations of catalysis and these other really important problems. Obviously, with the growth of DNA sequencing, there's this dream, right, of doing personalized medicine, but we're not really there yet, and where we want to go. And so with these recent trends of clock speeds no longer really increasing, running into communication bottlenecks and memory bandwidth issues, these recent trends have really favored sort of a return to special purpose hardware. And a fantastic example of this, I think, is the ANTON supercomputer, which I'm sure many of you here in the audience are incredibly familiar with. It won the Gordon Bell Prize here back in 2014. And what the system did, right, it was specially designed to run molecular dynamic simulations. But it really changed the ballgame. It changed what the simulations were able to do, taking those MD simulations from that sort of nanosecond timescale range up to the more biologically relevant microsecond, millisecond timescales to watch protein folding or to watch drugs actually binding with targets. And while this is really obviously fantastic work, when you do specialized hardware like this, right, you typically, whatever you're gaining in performance and capability, you're losing in flexibility, in portability, reusability, reconfigurability. And so our vision at Labs is to try and do sort of the next step beyond that, to do a little bit better. And what we want to do is to enable an ecosystem of computational accelerators that can be used in an architecture that will scale, from edge up to data center and beyond to exascale. There's sort of two main parts to that statement. The first is getting that one sort of scaling architecture. And this is what we call memory-driven computing. And you can see sort of a cartoon of what this looks like here. So instead of the traditional computer architecture, right, where data is sort of segmented into the amount of memory that a particular processor has and can handle, we're flipping that architecture around, and instead having memory at the center of the architecture, and then sort of democratically, any of your favorite traditional processors or your special purpose built hardware accelerators can all communicate to that same data stored in the memory. And one of the core technologies that really enables this sort of architecture to scale is the fact that we are using light. We're using photonic interconnects in order to provide the communication between both the memory and the processors, and also between the processors and other accelerators there. And I'll also mention here with this architecture, we're using the new open standard Gen Z protocol that some of you may have heard about this week. And what that allows us to do is it allows you to talk to all of your data as you would memory. So it's a memory semantic protocol, independent of whether it's attached via direct attached or a fabric attached memory. And so what this lets you do is then, right, have your computational accelerator that you've maybe specialized for your application, genomics, signal processing, but not only can you use that on a scaling architecture as your problem set size changes and your scale of your hardware changes, but also those computational accelerators could potentially be used across different applications. And I'll just mention really briefly here, this architecture has already shown some proof of principle demonstrations. This particular one was for transcriptome assembly with DZNE, which is the German Center for Neurodegenerative Diseases. I think I got the translation right, where they showed a 100x speed up of doing some of their large-scale problems just using this architecture. And so you all here are probably very familiar with these large-scale problems, but one of the other reasons why we want this architecture to scale is because we're also seeing sort of a really large need for high-performance computing at what I'll call the edge. When I say the edge, or when people hear the edge, they typically think of your mobile phone, right, and taking pictures. But in fact, it's a lot more interesting than that, or more rich than that. We've got examples of scientific instruments and satellites that are recording a huge amount of data. An example here for the DARPA Argus that is recording 6,000 terabytes of data, video streaming per day that it needs to go through and analyze. And we heard about the SKA as well on Tuesday that's generating a huge amount of data at the edge of the network. But not just sort of big data problems where you have a lot of information that you'd rather not have to pass back all of it to your network, but also doing machine learning and AI at a distance and at lower power budgets. You know, if we do want to think about space exploration and going to Mars, we're going to need robotics that are smart and that are able to learn on the fly without communicating with the cloud and back here on Earth. And so this is sort of our vision here, and what I work on in our lab is actually the second point that I haven't really talked too much about yet, which is creating computational accelerators that are better than what we currently have, but that are also flexible and reconfigurable at higher speed and energy efficiency. And that's a pretty tall order. And so in order to do that, we're turning to novel device physics and rethinking how we do computation outside CMOS to get there. And in particular, I'm going to be talking to you about our dot product engine, which is based on memristor technology in order to as an example for one of these accelerators. So this is sort of an overview of what I'm going to be going through with you today. Hopefully I've motivated significantly enough for you why we're looking at unconventional accelerators. I'm going to go through some just bare bone memristor essentials for what the building block core component is of our computational accelerator. Then I'll be getting into the guts of that, which is the dot product engine, the concept of it, where we are seeing the performance benefits coming from, and then our actual lab implementation of this system, as well as measurements and some data on its accuracy, some example demonstrations, ideas for the architecture, and where we think it matches up in terms of its overall performance, in particular for some neural network applications. And then at the very end, I have hopefully I should have time to talk to you about some very new work that is actually going even a little bit further, a little bit crazier, using chaos, controllable chaos within nanoelectronic devices in order to accelerate solving optimization problems. So first off, what is a memristor? Several people are probably familiar with this, but let's all get on the same page. A memristor is really just a metal oxide material sandwiched in between two metal contacts, as you can see on the left, bottom left there. And all you're doing is you're applying a voltage across those two metal contacts, and then you can control the resistance level, the resistance state of the device between a high resistance state and a low resistance state. And this technology is appealing for a couple of reasons. One of the first ones, which I'm showing here, is the fact that it's scalable down to very small sizes. And actually, it's been shown you can create devices that are less than 5 nanometers. What's shown here in the center image is a plug that's about 70 nanometers, and the thin film is about 10 nanometers. And then on the far right, you have a crossbar array. So what that is it's a grid of those memristor devices where in one direction you have all the top electrode contacts, and in the orthogonal direction you have all the bottom electrode contacts. That allows you to have a very dense set of array. Further than just sort of the scalability of this technology is the fact that it's non-volatile. And what this means is when I've programmed or I've set the state, the resistance state of that device stack to a high resistance state or a low resistance state, I can just set it and leave it. I don't need to be applying additional power in order for it to maintain its state. And in fact, it's been shown that the lifetime of these states can be greater than 10 years. And some of you are probably fairly familiar with the fact that this technology has been being developed for binary memory. You might have heard of RRAM, NVM, these kinds of things. But for my purposes, and what I find actually really interesting about these devices is that they're inherently analog. They're not just sort of a two-state device. They can have many, many, many states. And more than just many states, it can actually be continuously tunable in a very wide range of resistance. And one example of that is just shown here in this center plot. This is for 16 levels, but this is us tuning the resistance of a device from 2 kilo ohm to 2 mega ohm. So I have a span of 3 orders of magnitude. And we actually understand the continuously tunable analog capability of these devices very well. After taking a lot of measurements and doing a lot of modeling, we actually have really quite a nice model that explains the analog tuning in these devices is coming from sort of the changing local density of these Mott hopping states that are due to the oxygen vacancy sites. And what this model allows us to do is then forecast future performance of our different sort of analog computation schemes. So what about that analog computation schemes? What are we actually doing with these devices? And so this is the dot product engine, which is a memristor-based accelerator that is doing a vector matrix multiplication in hardware. And if you remember the grid of memristors that we talked about a few slides back on the right there, what that picture is in sort of circuit land and mathematically is shown there on the left. And so at each vertex between that top and that bottom contact, right, I have a memristor device whose conductance, indicated by G, there can be programmed. And if I have this crossbar array, and I, for example, apply a vector of voltages along the top electrode contacts and collect all the currents along the bottom electrode contacts, or apply a vector of voltages along the rows and collect the currents along the columns, what I've effectively done is a dot product operation. I've done a vector matrix multiplication. And just using the very simple physics of Ohm's law for that G times V to get a current, and Kirchhoff's law to sum the currents along the column. And we think that this sort of very simple architecture is really advantageous for a number of reasons for accelerating matrix multiplication. First off, we're using, like we just discussed, those memristor devices that are giving us a nanoscale, non-volatile storage for whatever matrix, conductance matrix I've decided to program in there. I have a high analog tunability there. But the main kicker here is that we're doing the computation where the data itself is stored, right? You can imagine that G matrix there is storing the weights of a neural network, for example, or a different kind of a computational kernel. And you're performing your multiplication and addition operations exactly where the data itself is stored. You don't have to fetch any weights. And that's really the key advantage of this kind of architecture. And the other thing that we're really excited about for this technology is that we see many pathways for scaling as we go forward in the future. And some examples of those scaling pathways are here: the array size, the number of memristor levels that we're actually programming within the array, and the surrounding circuitry, the DACs and ADCs are all ripe for improvement. So you might be saying, okay, I get this, but why are we looking at vector matrix multiplication? And there's really, as an example, two key applications that we think that this dot product engine could be really useful for. The first one is maybe not surprising to you guys, which is deep learning. So inherently within a neural network, right, you have some data. In this example, we have a picture of a building. We have our neural network that is telling us we've trained in order to recognize what that image is, and we're getting out, hopefully, building for that learned classifier. But especially if you think about a fully connected layer, as shown here on the top right, effectively what that layer is doing is vector matrix multiplication. That's what's going on. And in a lot of these particular convolutional neural networks, a majority of the computational time and energy is just these matrix operation. And again, the limit on the performance that folks have been really seeing is that data fetching, the fact that I have to go into memory or storage and get thousands, millions of weights and bring it over to where I want to do the computing. And so we think that the DPE dot product engine is a really nice fit here. Also because neural networks have shown that they don't really need a high level of precision, right? And so using analog computation in this kind of space is very attractive. Another key application for matrix multiplication is really kind of any linear transform, particularly in signal processing. And so this is an example here for doing Fourier transforms analysis, right? So you can effectively program into your memristor array the DFT matrix, give it some time-based signal input. In this case, it's just 2 sine waves added together. And once you do that vector matrix multiplication, what you're getting as your output is the frequency information for the system. And again, we think this is very attractive going forward for some of the same reasons. Also because here, this system is flexible. You can choose which frequency components you want to program into your system. Okay, so I've given you the concept and some interesting applications, we think, for why we want to do this, but what have we actually done? What have we actually built? And so this is our lab prototype that we have in Palo Alto. And currently what we have, because we're really exploring the space for what works and trying out different things, is we have all of our electronics in those PCBs off chip. And that allows us to test out a lot of different things while also exploring different schemes for that control circuitry. And then the center component is this chip that you can see here in the center that has many different sizes of those memristor arrays that are fabbed out. So we get these chips that have transistors on them, and we integrate in our lab the memristor layer going on top of those transistors that you can see in the top there. And what having a transistor memristor array really allows us to do is to very finely tune and program those memristor analog values. And you can see an example of this in the bottom right. So that is a 128 by 64 array of memristors that I programmed to the Hewlett-Packard Enterprise logo. And each one of those pixels is one memristor, and the grayscale that you're seeing there is the analog conductance value from 100 to 700 microsiemens. And further than just really being able to program those analog levels to show you sort of a nice image here, we can also reprogram these same matrices over and over again for different use cases. So I'm going here from the logo image to something a bit more useful, the differential DCT matrix that we'll be doing some computation with later on. And this is just to give you a sense that these arrays are really reprogrammable and reconfigurable as you change, say, the computation that you want to do within your system. This is over 8,000 memristors, and we're able to reprogram this whole array. I think this is showing 50 to 100 reprogramming cycles. So not only are we able to reprogram these large arrays and program them to these different analog levels, we're able to program large arrays very accurately, which has actually been a challenge technologically within the field. And we do this with a feedback tuning algorithm that you can see here on the left, which is showing you basically how we are moving around the conductance state of an individual memristor device whose conductance is given by that top plot, and we're aiming for a state within those two dotted lines. And the bottom two plots are showing you the voltages that we're applying to the device itself and also to the transistor controlling that device. And using this feedback tuning algorithm, we're able to get a programming accuracy of 6 bits within these large arrays, which we think is really promising. Okay, so we have these large arrays. We can tune them and program them very accurately and very efficiently, but how about the actual core computation? How are we doing in terms of actually performing vector matrix multiplication within this system? What does that accuracy level look like? And so we've looked at this for a couple of different kinds of computational kernels, both sort of sparse and dense matrices. And here's just 2 examples on the right there. Blue and red are for, one is for the DCT, discrete cosine transformation matrix, and the other is a single layer neural network for doing MNIST handwriting recognition. And what's shown in this histogram plot here on the x-axis is the normalized error. So that's the difference between our experimental measurement and what you would just expect if you did the multiplication out on paper or in software, and then normalized by the overall expected value. And as you can hopefully see here, we're doing, we have a normalized error generally of less than 1 part in 1,000, which is really, we're very happy with. And depending on the size of the array, we're getting computational accuracy of that vector matrix multiplication to about 5 or 6 bits. which we think is pretty good. So now that we've demonstrated we can do these multiplications in analog in our actual hardware system, how about some actual demonstrations for whether or not this works for a real world application? So one of the first examples of this is sort of everybody's favorite toy example neural network, which is doing handwriting digit recognition, right? So this is the MNIST handwritten database set, where the idea is you have a bunch of handwritten digits, and you want your system to be able to tell you if it's a 0 through a 9. And so what we did in this experiment is we just used MATLAB. We developed a single layer neural network to do this computation in software, translated it to memristor conductance, programmed it within our memristor array, and then did the full computation. And so you can see some examples for 3 different digit images at the bottom there for number 4, number 9, number 5. And we're comparing the software results in blue for what that vector matrix multiplication would give you, and the resulting classification results, compared to our experimental result with our DPE system in red. And as you can see here, we're doing pretty well. And when we do this classification test over the full 10,000 images of the MNIST test database set, we get the recognition accuracy shown here on the bottom right as a function of, this is a function of digit. But when we compare it to how we would do in software, we think that we're doing pretty well. So if you just use this single layer software network within my computer, we would get 92% accuracy over that full 10,000 image test set. And in our experimental case using the dot product engine, we got 90.1%, which is really pretty good, we think. And we understand also where that gap is coming from. It's coming from, we basically have some stuck on and stuck off devices. If you look at that image in the top right of that matrix, you can probably see some bright red and bright blue spots that aren't supposed to be that bright red or bright blue. And we're getting this result really without any further schemes that we've already sort of thought about improving this, this kind of application using redundant columns and different kinds of error correction codes. So we're pretty excited about this application. Another application for a lab demonstration for the DPE is again doing that, using that discrete cosine transformation matrix in order to do signal processing. And so here, as an example, we have different time-based inputs coming into the system, which are all sine waves of different frequencies. And when we compare the experimental results and the results you would again expect from software, just doing the multiplication out, we get very nice results. So not only doing just 1D time-based systems, we can also do image processing. In fact, this one is interesting because we're able to do computation of several convolutions in parallel. This is an example where 10 different 5x5 convolutions were taken, unwrapped, programmed into the memristor matrix, and then using the canonical image, Lena image here, we're able to compute these 10 different filtered images in parallel. And this obviously changes sort of the number of operations that you need to do in order to do your task, which is interesting going forward. So these are some nice lab experimental demonstrations, but how would you actually use the dot product engine in a real world system, in a scaled up system? And so some of our colleagues have done some work on this and thinking about how this kind of dot product engine would work in a full architecture. And for the purposes of this, the XB that you can see in this tiled architecture here, XB stands for crossbar, which you can think of as the dot product engine here. And this architecture was designed and tuned in particular for convolutional neural network inference using the DPEs. And they also figured out a fun way that they can actually have dynamical variable precision. But from the results of this work, they showed that you could actually get a speed up of 15x, an improvement of over 5x in terms of the energy compared to the state-of-the-art digital ASIC for doing CNN inference, which was pretty promising as well. So if we want to think about top-level performance, how using something like the dot product engine compares to other ways of doing computation today, it's a little tricky to do benchmarking because this is an analog system and it's doing things a little differently. So we've tried to look at this a few different ways, so bear with me. The first way is if you just look at the discrete operation level, right? When I do vector matrix multiplication, I'm doing a bunch of multiplies and accumulates. So if I think of it just in that context and the raw matrix multiplication value we get with some reasonable ADC numbers and 150 megahertz, we're getting 115 teraops per watt, which at least the best comparison that we've found so far is a 16x improvement over a digital ASIC at 40 nanometer CMOS that was reported in this paper here, which we think is pretty promising. But how about the application level, right? That's sort of where you actually want to benchmark and compare yourself to. And so for this, we're looking, this is going to be utilizing that ASIC architecture I just showed you on the last slide that is specifically designed and tuned for convolutional neural network inference. And when we first did this benchmark comparison to the state-of-the-art digital ASIC, right? Those numbers that I just mentioned on the previous slide got a 15x speed up and over a 5x improvement in energy. And at the time, that state-of-the-art ASIC had been benchmarked to the NVIDIA K20 and showed sort of a 450x improvement speed up and a 150x improvement in energy. And so that's where we were when we did some of this initial work. And obviously, NVIDIA and Google and others haven't stood still, right? And so since then, the TPU has come out, obviously, and it's shown a 15 to 30x speed up over the Kepler GPU. And we also have the Pascal GPU has had a significant speed up as well over previous generations. Although some of those speed ups are coming from sort of one-time improvements, right, going from 32-bit to 8-bit precision and things like this. And also at the same time, we haven't stood still either. So by doing some simple work improvements on actually just the surrounding circuitry, the ADCs in this architecture, we've also shown continual improvement in our architecture. So the DPE based architectures is still showing a significant speed up in energy improvement, we think, over sort of state-of-the-art what we have today. But even a more particular point that we think is promising is really just where the future scaling for something like the dot product engine can be going. We have many avenues for continuing to improve this prototype. So just to sort of summarize what I've hopefully hammered home with you today for our computational accelerator for matrix multiplication that's based on Memristor technology, we've shown we can get speed up and power reduction for really some core key applications. But hopefully you're also getting the fact that we're getting that improvement a lot because we're doing the compute in memory, because we don't have to be fetching constantly our weights or different values that we want to do the computation with. And so with the last couple of minutes that I have left, I'm now going to take you even a little bit further afield and a little bit more out there, which is using controllable chaos within nanoelectronic devices combined with our dot product engine accelerator here in order to accelerate solving optimization problems. And so what I didn't mention earlier when we went through our really quick Memristor essentials was the fact that in addition to the other characteristics of Memristor devices that I mentioned, Memristors can also behave like neurons. And in fact, so this is a very simple sort of different kind of memristor device that's based on niobium oxide material that displays negative differential resistance. So in this plot here, I'm applying a constant current and I'm watching the voltage, and that bend back you see in the red curve there, that's NDR, negative differential resistance. And what this indicates is that your system has local activity. It has the ability to amplify energy. And this has also been hypothesized for how computation is really being used in the brain as well. And using this memristor element of the NBO combined in a circuit, you can basically get and directly emulate the signals that we see in the brain from neurons. So there's 3 examples here for spiking and chattering and these kinds of things. So on top of that, when we scale these devices down to nanometer length scales, we've also seen that they can exhibit controllable chaos. So this is very new work that was published just a couple of months ago. And what my lab mate showed was that by very carefully tuning the voltage applied to the device and measuring the current through the device, he was able to show that current through the device, that behavior went from a very kind of regular type behavior, showing those oscillations, to then showing chaotic behavior, as shown in red there for the 1.03 voltage value being applied. And so what we wanted to do with these kinds of devices is to then say, okay, what can we do with them? How can we use them to compute? And our first kind of just example to get us going was to then think about doing, combining that chaotic behavior with our vector matrix multiplication in the dot product engine in order to create a full system to solve an optimization problem. And so the first one we've done is to basically encode a Hopfield network. And the problem that was initially chosen was the traveling salesman problem, which hopefully everyone here is familiar with. You have a number of cities and you want to find the shortest route to measure all of the cities. And this traveling salesman problem can be encoded in a Hopfield network and an energy minimization problem shown by that equation there, where you then iterate, and the goal, right, is to find the global minimum energy in the system without getting stuck in that local minima. And so what we did was basically encode this energy minimization within the DPE, but then use the threshold for the update rule as where we injected the chaotic behavior from the niobium oxide devices. And our example solutions are shown here. So in the top plot there is shown how the system behaves when you have no chaos. So you're not changing that thresholding element when you're doing this iteration for energy minimization, compared to when we do inject chaos into the system in red. And you can see those 2 solutions in B and C there as well. Obviously, the B solution actually doesn't even satisfy the problem. This approach was also run over many different iterations, exploring randomizing sort of the order in which you do the update rules and these kinds of things. But we were able to reliably show that by injecting chaos into the system for this problem, we're able to find a statistically significant lower Hopfield energy and a lower problem solution. And so if some of you are familiar with simulated annealing approaches to these kinds of things, this will be familiar to you. This is really just using the dot product engine plus the controllable chaos within the niobium oxide devices in order to make a simulated annealing machine in hardware. And so this is kind of just a brief summary for what we've done with this second part of for where we want to go with using the dot product engine. We're again using the novel device behavior in order to do computing in different ways so that we can do it faster and at lower energy. Although in this case, this is sort of just work that's starting. So we've started with the Hopfield network, but know that there's many other possible things that we could do. So with that, I just want to sort of hammer home some of our top points here that I've hopefully chatted with you about today. Using novel kinds of devices in order to do compute, not in CMOS, but in different ways. But hopefully I've convinced you that there's some promise to these approaches. And also future scaling for this technology beyond where we think CMOS is going to start to slow down. And there's a lot of work that's gone into sort of developing this system, and so I really need to acknowledge our team, and in particular John Paul Strachan, who is our group project lead, and Miao Hu and Suhas, and many of these other people who have done a lot of the work that I've shared with you today. All right, thank you.
So we have a time, take a few questions. So if you have a question, please come to the mic. Yes, number 2.
So what are the programming times like on the Memristor array and growth? How big can I make these? What's the prototype size?
It's a good question. Very good question. So programming time currently is mostly limited by the fact that we have all our control circuitry in PCBs, and we have a microcontroller, and then we have our lab computer that tells the microcontroller what to do. So if you looked at the whole system, you know, it's not very impressive. But when you get it in chip, it's pretty good. So we're using 100 nanosecond pulses in order to program those devices. And, sorry. So yeah, I'm not sure I'm able to answer your question for what a real world implementation would be, right? This is a lab prototype, but is definitely something that we're looking at as we move towards putting those electronics in chip.
How big do you think you can make them?
Okay, so that's a good question. The better thing that's actually been shown in the architecture studies is when you're creating an architecture, you might not actually want them that big. So the ASIC architecture found that a 128 by 128 was an ideal size for the convolutional neural network, and we have 128 by 64 currently out. What I also don't know is probably we're going to be able to make larger ones as we scale down. So that's a 128 by 64 and a 2 micron kind of technology in our lab demonstrations. But I don't know. We have. I'm not a transistor chip person, but we certainly looked at scaling them larger. Yeah.
Okay, number 1, please.
My question is that it seems you used fixed point for the dot product, but for large neural networks where the kernel size is big, how do you handle the overflow problem?
But I don't know.
So the dynamic range.
I'm not sure I understand.
So because of the fixed point, 6-bit fixed point number can only represent.
So that is one thing that computation was done in the analog domain, right? So it doesn't, the precision is controlled by your ADCs and DACs to some extent. But what was shown in the ASIC architecture is by using some simple shifts and adds, you can actually have dynamical accuracy. So you can use and tile that architecture and get whatever dynamical precision you want and whatever your application requires. Does that make sense? If you're interested, I'd encourage you to look at that architecture paper. It's quite nice.
Okay. Now how do you handle the temperature change on the analog circuit?
The what change?
The temperature change.
The temperature change. So that's where that model that I mentioned probably about halfway through really helps us out. Because we did a lot of measurements of these devices, actually from 100 to 700 Kelvin. So we understand very well how they behave with changing temperature. There is some increased noise with a little bit increased temperature, but that is something that having the accurate physical models really helps us helps us understand and handle.
Thank you.
So last question, number 2, please.
So the ASIC architecture you showed was very focused on inferencing of the neural nets. And I'm wondering if you could make any comments about work you're doing with trying to implement on-chip training of the neural nets as well.
Training is sort of the next key step. I didn't talk about it here because it's work that's about to be submitted to a conference, but we've also done, or not we, an intern that we had this summer, and John Paul and a few others in labs did some work generalizing the architecture. So that was the first step, which was saying, okay, not just for CNNs, but for other kinds of deep learning networks, for doing recurrent neural networks, LSTM, how can you generalize that architecture, and what do you lose potentially in performance as a function of that? And so we've done a significant amount of work for that. For the training, our first next step there, I think, is the materials. So we really have been doing some more materials work in order to get better, what we think are better devices that will sort of change linearly in conductance when you apply that delta V in order to do that. But that is the next key step. So the advantage now is that we have this prototype, and we actually have another 2 prototype systems so that we can start doing these experiments and collecting the data in order to do that development for training. But that's something that we're certainly thinking about for sure.
So if you have a quick question, so please come to her by the frame. So thank you for interesting talk.